Yeah, I'll take lab reports. So if anyone wants to hand in lab reports right now, I will take them. I will also take homework, but you can give it to me on Thursday during recitation or anything else. I think that's all we have.
Am I supposed to get them on Blackboard? Do I need to still give
The
it?
homework?
Yeah.
Yeah, then you're fine.
Okay.
I just haven't checked them yet. And you can also turn your homework in on Blackboard online. That's fine. Yeah, and I put out the Chapter 3 homework a little early for you guys, so you wouldn't have to wait until recitation. I'll take anything that you have.
Balancing equations.
Familiar stuff, or?
Kind of. I was in basic chemistry in high school, so.
That's good. You should be prepared. All right, let's go ahead and get started. Are there any questions or anything before we begin? Any logistical concerns? Yeah, so the homework, you can just give it to me after class. You can also hang on to it and give it to me during lab or recitation. I'm not too picky on the due dates, plus or minus a couple of days. So I don't mind. I'm just trying to get stuff, because the sooner that I get stuff, the sooner that I can start grading and try to give it back to you. So that's the only thing that I'm trying to do here, is just keep at least flow going, so you get feedback, whoever is, turning in stuff, and I'm not delaying too much, because I know I will get behind if I don't actively stay ahead of things. And so we have our second lab this week. So there'll be some measurements, introduction, so you'll do more sig-fig practice today or tomorrow, or Thursday, I mean, so either today or Thursday, depending on your lab. And then those of you in the Tuesday lab, I'll do the exploding balloon demo for y'all today, so you can enjoy that. All right, so let's start diving into how to name things. And so just, you know, kind of a word of caution or a word of encouragement is the beginning of chemistry, everyone kind of goes in a different order. I'm not quite satisfied with the way your textbook does things, but this is just the order we're doing them. And so just kind of bear along, you know, hang on for the ride. If you have questions, ask questions, you know, stop me. Because again, everyone's at a different level in this class. And with especially the beginning of chemistry, it takes a little bit so that we're all kind of speaking literally the same language of chemistry, and we're all on the same page. So we're still working there. And so with that, we're going to shift gears and talk about how to name things and how to name our compounds. And so we're going to start with ionic compounds. And so these are the easier ones to name. And so we'll look at two different types. And so we have two types of ionic compounds, and those are going to be metals that form only one type of ion versus metals that form more than one type. So let's first distinguish these two. And so all this is saying is, so the metal that forms one type of ion, those are going to be, and you can look at your periodic table, and then we'll kind of help you. But so these group 1, they always tend to be in the 1+ oxidation state. So again, just hang with me since we're all over the place on these terms. But what this is saying is these alkali metals, and we'll later go in depth on this, but they tend to just lose one electron, really reactive. But that just means that they're only going to be in this 1+ oxidation state. So same thing with this group 2. So this is always 2+. And so we're generally looking at groups 1 or 2 for the type of metal that can only form one ion. And then sometimes we can also include these two guys. I'll highlight them. And then there's a few other exceptions like zinc and silver tend to just form one type of ion. And so these over here, aluminum and boron, they will always be in the 3+ state. So we'll later learn that these will have 3 valence electrons. Zinc, so if you have your yellow or whatever color beige periodic table out, that should also help you. So hopefully it just says 1 oxidation state for zinc. And that kind of gives you a hint. So zinc is always 2+. And then silver might have different oxidation states on your periodic table, but we usually assume that it is 1+, and that is generally the most common state. So usually you don't indicate it. So now going back to these rules. So again, metals that form only one type of ion, right in there, generally group 1 and 2, and sometimes group 3, and we have exceptions. And again, put some examples, so sodium, potassium, magnesium. And so the compounds that we're going to be naming are going to be like sodium chloride, potassium chloride, magnesium oxide. And then, so what does this mean, though, if a metal forms more than one type of ion? So if you look at your periodic table, and then you look at the transition metals, there's a reason why intro Gen Chem generally doesn't like to tackle the transition metals. But that's all because these have variable oxidation states. And so if you look at your periodic table, so I don't have mine. Yeah, I'll steal yours for a second. So if you look like iron, for example, in the upper right-hand corner, it says +6, +3, +2. And those are just the most common 3 oxidation states. So iron can be in like the 1 oxidation state, the 3, the 4. So cobalt, it should have listed way more for that. So cobalt only has +2, but cobalt likes to be in the 3 oxidation state and the 1. And so it has others on there. So chromium, it lists +6, +3. Manganese, so +7, +4, +3. So it kind of gives you an idea, again, of which metals are going to have variable oxidation states. And we're not going to go into why today, but just kind of appreciate that they have a bunch of d electrons. That means that they can give up different numbers of electrons, take different geometries, all those things. So anytime you see a transition metal, you know that that's one of these, a metal that can form more than one type of ion. So transition metal. And then there's a few other exceptions. So it lists them here. So the inner transition metals and the p-block metals. And so the p-block metals, and again, your periodic table should help you, but I'll highlight them. So lead is one of those. So it's either in the +4 or the +2 oxidation state. I believe tin is another one. So that's also +4 or +2. So generally those two will be your variable ones. All right, so let's name them. And so we're just focusing on these binary ionic compounds. So all binary means is we have two different elements, so we're keeping it really simple for now. And so the names of your binary compound take the following form. So you just name your cation, and that should be your metal. And your cation is always going to be positive. And then you'll add to that the base name of your anion. And so let's say we're trying to name potassium chloride here, KCl. So we name potassium. And then it says take the base name and then change the ending to "ide." So we can look at chlorine. So it's chlorine. And so chlorine becomes chloride. And so we can do some other examples. So we have calcium oxide. So go ahead and name these. Scroll back here. All right, so look at those 4 examples. Take a minute or two, and we'll go over their naming. All right, let's start naming them. So SRF2, what is this? So strontium fluoride. And then, so how did I know, by the way, to put 2 fluorines there? And then how would, this also asks us, well, how would we go back? What if we were just given the name strontium fluoride? How would we write the formula? Yeah. So exactly. And so if we look at our periodic table, and so eventually we'll start putting these numbers everywhere. So we said that this group likes to lose 1 electron, this group likes to lose 2. So there's strontium. So that means it's donating 2 electrons to something. And then so fluorine, if you want to write in the halogen, so I would put a -1 over here. So this means they tend to gain 1 electron. And again, we'll delve into the why as we go on. And so oxygen's -2, nitrogen's -3. But the whole key is, so when we write our compounds, is that we have a neutral salt. And so just like you were saying, that means that when we write our formula, we have to write it such that these charges balance out. And so if we know that strontium tends to be in the 2+ oxidation state, we know that we need 2 equivalents of fluorine to balance that out. That means 2 individual fluorine atoms are each getting 1 of those electrons. And so we get our formula back out.
Would calling it difluoride just be like redundant, I guess?
Yeah, because it's not necessary, because we get that just by saying strontium fluoride. We know the formula. And then using like the prefixes of di, we'll get into, but that's more for molecular compounds. Since we'll see with the molecular compounds, you can have different combinations of like NO, NO2, N2O3, so you would need the prefixes to indicate, since we can't tell. And so that's the key distinction between the ionic compounds and the molecular compounds, is that you can tell with the ionic because they're going to have charges, and they're held together by their charges too. And I'll bring up kind of a tricky point, but you should be able to like look up these different crystals. And they will make what's called these crystal lattice structures. Oh my gosh. And what I mean by that is, so strontium fluoride, you never have a distinct just molecule of strontium fluoride. It's just these repeating units in this crystal lattice structure of 1 strontium to 2 fluorides. So you can see that there. And so that's kind of the distinction as well between an ionic compound and molecular. All right, so what about the next one? Rb2O. So rubidium oxide. So again, same thing. So if you look at rubidium, it's in our group 1 over here. So it tends to be in the 1+ oxidation state. Oxide is located in this group, group 6. Those all tend to want to gain 2 electrons to fill up their octet rule. So that has a -2. And so when you go back, going back from rubidium oxide to our formula, we know we need 2 equivalents of rubidium to balance out that oxide. So questions on that one? And again, oops, oh my goodness. I'm trying to belabor this point. So again, rubidium oxide. So this is what this would look like in its crystal lattice structure form. So again, no distinct, just rubidium oxide alternating Instead, we just have alternating units of 2 rubidiums to 1 oxygen in here. And they all take different forms. All right, next one, so Kbr, Potassium Bromide. And so this one, they're in that 1-to-1 ratio, so we can go back to our periodic table. So potassium is, of course, in group 1. Bromide, or bromine, is over here in our halogens. And so they are balanced. So potassium tends to be 1+, bromine 1-, so that gives us our 1-to-1 ratio of Kbr. And so there's, again, its crystal lattice structure. All right, and then our last one here, so aluminum chloride. Oops, I gave it away. That's what happens when you do too much chemistry. So I gave it away, aluminum chloride, but I actually wanted to point out an exception here, because aluminum chloride, you could kind of argue with me. And so what I mean by that is some people would maybe argue you should call it aluminum trichloride, and that is because it is not a true ionic compound. So it is named like an ionic compound. We treat it as such because aluminum is a metal and chlorine is a nonmetal. So again, we assumed that they would just make an ionic compound. But this is one of those funny things about chemistry, is that there are always exceptions, and I wanted to just point this out because this is the true structure of aluminum chloride. And so you can see it actually makes this kind of dimer form. So there's 1 aluminum trichloride, and so it has some sort of repeating. So 1, 2, 3 chlorines, 1, 2, 3. And so this is its structure, and because of that, you could argue that it's really a covalent compound and should be named as such. But for naming purposes, people just refer to it as aluminum chloride, but you will see aluminum trichloride. That's where the discrepancy comes from. So does that make sense? Not trying to confuse you. And you can see even on the Wikipedia, right, they even name the oxidation state, which I just said don't do, and they call it trichloride. So there's a reason why, though, that it is that way. So for our purposes, again, we're just kind of treating it like an ionic compound for naming. Oops, did I not do examples? Okay, so now let's do the other type. So our elements with different oxidation states, or ionic compounds. So ionic compounds. With variable oxidation states. Yeah, so ionic compounds with variable oxidation states. So now, how do we name them? And so the general kind of rule for it is that we'll have our metal cation again, so whatever name that is. And then in parentheses, we need to put the Roman numeral of its oxidation state. And then the ending is just the same, so then your base plus the ide. And so let's see what do we mean by oxidation state, and how do we determine that? And so we're looking at 2 different compounds. And so right away you can see the issue with naming it. So we can't just call it iron oxide, because that doesn't give us enough detail. These are both iron compounds with oxygen. And so now we have to ask ourselves, well, how do we determine the oxidation state? And so we know our salt has to be neutral. So what you have to do is, based off of the other atoms, what must its state be? And so in this case, we have iron and 1 oxygen. And so what's the oxidation state of oxygen? So -2. And so if this is -2, and right, we're not going to add any subscripts or anything. It's already balanced, so we just need to balance it by indicating the oxidation state. So what must the oxidation state of iron be? +2. And then so for this one, we would write iron in parentheses 2 with our Roman numerals, oxide. So now try it for this one. So what do you think the oxidation state of that iron is now? So what's the oxidation state of our oxygen again? So -2. So we could set up like a formal math equation. So we know there's no charge indicated, so it has to be overall 0. So 0 is equal to 2 times x plus -2 times 3. So what's x? So x equals 3. And so this is how you would formally set it up. You can also do what I call this little swap trick. And so the other way to do that is you can back out these subscripts and see if they match your oxidation state. And so you can back them out. And what I mean by that, if this is 2, this should be -2, and if that matches, this is going to be 3 plus there. And so you can see this would be the same as kind of writing out this whole variable, because you could start off with 0 is equal to 2 for your iron times x plus 3 times y for your oxidation state of oxygen. And so the easiest way to solve this, though, is just by swapping these two subscripts, and so that matches with our oxidation states. And this would probably make more sense, let's say, if you were doing the opposite. So if you wanted to write your formula, so let's say you had chromium 4 oxide, and you were trying to determine the formula. So you could write chromium has a +4 oxidation state, oxygen -2. And so the easiest thing is to swap them. So this becomes a subscript for chromium, this becomes a subscript for oxygen. And then I wanted to point out this example specifically because it will fail you slightly when you have this like 2-to-4 ratio. So the other thing is you want the lowest whole number ratio, right? Unless you know that the formula is a dimer or something. And so when you see this, oh, okay, I should really divide by my lowest common denominator to give us chromium CrO2 like that. So then going back to this example, we just want to write our name properly now as iron 3 oxide. let's do a few more examples. So try this compound. So what would be the name for this one? WCl6. So I hear a tungsten. So that's our W. And then what do I need to indicate? So what's the oxidation state of tungsten? So I hear a 6. So yes, it should be 6 plus, right? Each one of those chlorines is -1, so -1 times 6, so overall -6. So then if it's +6, how do I indicate that? So Roman numeral 6, so tungsten 6 chloride. And then take a minute or so. Manganese 3 oxide, how would we write that formula? So did we get a formula? For manganese 3 oxide? So I'm hearing different things. So let's start kind of at square zero. So we have manganese, we have oxygen, right? We at least know that much. Then this 3, what is this 3 telling us? So the oxidation state, right, of our manganese. So I'm going to write this 3 plus up here. What's oxygen's oxidation state? So -2. So the easiest thing is, again, setting up our algebra. We could have 3 times x plus -2 times y. Or we could easily just swap them. And so I'm just going to take this 2 down there, this 3 over here. And so double check. Okay, that balances. So 3 times 2 is +6. -2 times 3, -6. That gives me an overall neutral compound. And again, there's no charge indicated. And so that looks good there. And so again, just make sure you're balancing the oxidation states. So just start with, I know my oxidation state of manganese. I know it of my anions, in this case oxygen. And you can solve. Let's do one more. So palladium 4 chloride. And do we have a formula for this one?
PdCl4.
So I heard it several places, PdCl4. So good. So palladium is in a 4+ oxidation state. Chlorines are always -1. So you needed 4 chlorines to balance that out. Yeah.
So how do you know, just based on the oxidation states on the periodic table, which would be applicable to chlorine in this case, because it's got +7 +5?
So for those, I know your periodic table's like trying to help you. In our case, when we're naming, just look and assume that the halogens are -1. So I would like write this on your periodic table if you haven't already. So I would write your oxidation states. So our group 1, our alkali metals are 1+, group 2, alkaline earth 2+. Skip over to group 3, these are 3+. Carbon gets weird, so they can be 4+ or 4-, so I just kind of ignore them. And then group 5, now we're getting closer to filling up our octet, so this is always -3 for the most part, always -2, and always -1. And yeah, we probably wouldn't approach any of those weird oxidation state scenarios, because why it's telling you that is because there's different compounds that can be made that are like just covalent compounds, and then formally they take different oxidation states. Oh, one I forgot to mention, some more exceptions. So the only thing that might come up that would throw you off is what are called hydrides. So you could have this sort of compound, and usually hydrogen is going to be in the 1+ state, but hydrides are an exception. And so all a hydride formally is it's generally a hydrogen bonded to a metal. And in that case, it will have a -1 oxidation state. But there aren't too many metal hydrides that will come up. And so what would the name of this one be? So aluminum hydride. And so you could have like iron hydrides and any sort of other combination. Any question on these ionic compounds? So either just the most common form, so our metal form with one type of ion, or our variable metals. Questions? And so let me know if anything crops up. So now we'll kind of transition now to our molecular compounds. And you can add to this covalent, yeah.
Manganese, is that +7 oxidation or 6?
So it could be anything. So manganese tends to be in the +7 oxidation state, but that being said, it could take other states on there. And so now these are our covalent compounds. And so we will have our prefixes. So now we're going to do what you said you wanted to do, is can we just indicate using our prefixes how many there are? And so that's what we're going to do for covalent. And it makes more sense for covalent compounds than ionic, since I think we've mentioned it before, but we could have like CO, CO2, NO, NO2, N2O3, N2O5, so many combinations. And how the heck do we distinguish between all this? We can't just say carbon, oxide, or anything. That doesn't help us. And so for covalent compounds, we use these prefixes, and I find it a little easier to name covalent compounds. So all we do is we have our first element, and the prefix. If we have only one, we generally don't say mono in the beginning. So for CO, so let's say we want to name CO, we don't say monocarbon monoxide, we just say carbon monoxide. And so you see we have all these prefixes, so mono, di, tri, tetra, penta, hexa, hepta, oxa, nona, deca. And you could look up higher than that if you needed it. And then again, we change our last element to the "ide" ending. So now let's name all these. So CO2, carbon dioxide, so what is NO? So nitrogen oxide, NO2, so nitrogen dioxide, what other ones did I put into O3? So how would you name this one?
Be dinitrogen trioxide.
So dinitrogen trioxide and N2O5. So dinitrogen pentaoxide. And so notice with the naming too, so we had pentaoxide, but that would give us kind of two vowels, so they just tell you to kind of drop the A, so it's pentoxide. But I try not to be too picky with little naming things like that, so just do your best, at least make it so where I can tell what the element is. You know, I'm not trying, again, to kill you over spelling. All right, so hopefully that was straightforward on the covalent compounds. We could go crazy, you know, naming them. Like, where's my mouse? There we go. So we'll do one more. SF6, so what would this be? So I heard a sulfur, and I like the hexafluoride. So sulfur hexafluoride, this is cool. I just wanted to bring this up. It's a gas, but so everyone's pretty familiar with helium, right? How it makes your voice higher. So sulfur hexafluoride does the opposite. So it's much heavier, so it's more dense. And so if you were to breathe a little bit of that in, you would get a nice deep voice. So always practice safety measures though when breathing in gas, because you could, obviously you don't want to displace too much of your oxygen with any gas. All right, so now,
Could
yeah.
both heat have the same prefix, like 5 nitrogen and like 5 oxygen?
Yeah.
Would it be like penta nitrogen and pentaoxide, or what? How would that be?
So the question is, could we have the same prefixes? Like, that would show, that could happen. I just can't think of any examples off the top of my head. Yeah, because you do have like So there's a couple of things with what you said. So there is a compound, I think N2O2. It's just usually with the formula, you just want to make sure that your compound is representative of an actual molecule. So as long as it actually exists, that it's like 5 oxygens and 5 nitrogens bound, like there's nothing wrong with that name. So in this case, right, for this one, it doesn't matter that there's 2 of them. We can still write dinitrogen, dioxide. It looks funny. And if we had your scenario, right, 5 nitrogens, 5 oxygens, so penta nitrogen, pentaoxide. It's just this normally doesn't happen because again you'd have to have some sort of crazy structure like that. But I'll just add this as a theoretical. So I don't think it exists, but yeah.
Why is it carbon monoxide and then when it's nitrogen it's only nitrogen oxide? Like why is it not monoxide?
Oh yeah, we should have put nitrogen monoxide. That was my bad.
Oh, okay, I guess
So nitrogen monoxide. Other questions? Anything else I messed up on? And so now, kind of the next thing that we need to go over and make sure we're all on the same page on is formula mass and how to calculate your mass. And really this is one of the most important things that you'll do as a chemist. And especially if you do like synthetic work all day, every day, that's what you're going to be doing is what's my molar mass of things. And then you're going to be doing a bunch of stoichiometry. And so we have formally our 2 different definitions. So our molecular mass is the mass of an individual molecule or formula unit, and this is the mass of 1 mole. This is also the same as their atomic mass, and we can go into why that is. But if we look at our periodic table, so if we look at this number here, so not only does this correspond to the mass of 1 atom, so 1 atom of carbon is 12 atomic mass units, it's also equal to a molar amount, so 1 mole of carbon is going to be 12 grams. So this would be either the molar amount or the atomic amount. And so that's all that it's saying here. And so anytime we want to get the mass, all we have to do is add everything up together. And again, this gives us both the mass of 1 individual molecule of water in atomic mass units, and also the amount that 1 mole of water would be. And so all we did was grab our numbers from our periodic table. So if we have H2O, we know we have 2 hydrogens, so 2 times, and you could use 1.01. This is where, it's kind of up to your discretion whether you want to use that or 1.008. Sometimes I just round to 1 if I'm feeling lazy. So 1.008 plus, you can either use 16, or if you look on your periodic table, it might say 15.999. And it doesn't matter too much, but you'll see that there'll be slight discrepancies in numbers. So add that up, 2 times 1.008, 15.999. And so I kept all my sig figs so I could report it to 18.015. And again, that'd be grams per mole or atomic mass units. For 1 individual. Let's do some more. So see if you can get the mass for this compound. So see if you can name it too. So name it tally up the mass. So ionic is going to be a metal plus a non-metal. So again, anytime you see those groups like 1 and 2, or groups 3, and then any non-metal. So any non-metal is anything on here on the periodic table. So what's the mass of silicon from our periodic table? So 28.
Yeah, 28.086.
So 28.086 plus 4 times, what's our chlorine mass?
35.453.
And then while I'm tallying this up, how would you name this? You said silicon tetrachloride? So silicon tetrachloride. Excellent. So silicon tetrachloride is a pretty nasty fuming liquid. So it reacts pretty readily with water in the atmosphere to make silicon oxygen bonds. So it likes to make, that's essentially glass, SiO2. And it also makes HCl, so it's quite fun to work with. All right, so did we all get 169 about? And so it looks like I can keep my sig fig, so 169.898. But again, some rounding is acceptable depending on what you picked. Let's do one more. And so I will tell you, so this is nicotine, formula for that. So C10, H14, N2. So see if you can tally that up. Do we get a mass yet? And so you can, I'm just kind of rounding, so 10 times 12 plus 14, since each hydrogen is about 1, plus 2 times, what's nitrogen, 28, or 14, I mean. And so what do we get from the mass, roughly?
About 162.
So 162. So I'll get that. So excellent job there. All right, any questions on this? Yeah.
Would there be a special prefix for 14 hydrogen?
I would honestly have to look up the prefix. But for these, like, they wouldn't be named like that. So organic naming, gets crazy. And then, especially if it's just like a known molecule, like nicotine. I'm trying to see if nicotine has another name, but it just becomes hard to name since with organic chemistry, a formula isn't very reflective of the structure.
Is that why they name it like nicotine? And
Yeah. Yeah, and then, I mean, if you stay like the course of this 200 series, we'll talk more about organic naming in the end, so then you'll get like more of a flavor for how to treat. Like we mentioned, I think alkanes in here, so those are easier to name, and then kind of building up groups in OChem. But that's a whole nother lesson of how to name OChem compounds. All right, so let's keep marching on. And so now, and this is where I feel like we're bouncing all over the place. So we look back at our elements again. We know how to make compounds, and now we want to go back, and we're going to focus on the atomic structure and kind of the details of that and how we got everything. And so we'll start with the discovery of the electron. So this was really one of the first fundamental particles that they discovered. So they have an atom. And so J.J. Thomson started doing these cathode ray experiments. So a cathode ray is just essentially a neon light. So first he just started, he has a neon light going, and he can see that he can, pass electricity through some gas. It makes a nice line going in this cathode ray tube. So then he was wondering, well, what happens if I try to put a field to it and a magnet? How will I affect that line? And so what he was able to do is then he created an electric field, and then he noticed that if he applied a negative charge to it, that repelled the beam. So first it was straight, he has a negative charge, now it's repelled. So now he's understanding that he has some sort of beam that's made up of negatively charged particles. So that was kind of the key point from J.J. Thomson's experiment. So some sort of small particle with an electrical charge. And then he was able to measure the mass to charge ratio of cathode ray particles by deflecting them. So like I was saying, he's using electric and magnetic fields. So applying them, releasing them, seeing how much that would affect the angle of the beam. And so he got about negative 1.76 times 10 to the 8 coulombs per gram. And so again, here's the cathode ray experiment. So just running charge, an electrical current through a tube. And so we have neon lights in our labs. You'll get to see kind of what that would look like. But that's basically what his cathode ray tube was. And so you can see there's a beam. Obviously, those are the beam of electrons. And then he had a setup. So now he created an electric and magnetic field to deflect and play with that electron beam. And so, okay, we have an electron. And so we know that we have some sort of negatively charged low mass particle present. And so they were still trying to figure out kind of the mass and the charge of an electron. And so from this, Millikan took the next step. So Robert Millikan set up what's famously known as the oil drop experiment. And so what he did, he has this little atomizer to spray out little droplets of oil. And then based on the size of those droplets, you could get kind of the mass of those droplets. Then you have a positively charged plate. Then he passed these droplets through his field here, so to a negatively charged plate. And then depending, again, on the field he would apply, he could either kind of suspend them and then, or make them move. And so from there, he was able to determine the charge and the mass. So experiment, we want to measure the strength of the electric field required to halt the free fall of the oil drops. So again, that's what he did. You have your oil drop that was charged. And then, again, determine the mass of the oil drop from their size and density. And so from there, he got a very accurate result. So the charge on any oil drop was always a whole number multiple of negative 1.6 times 10 to the negative 19 coulombs. And so Millikan was successful in getting the fundamental charge of a single electron. So very cool how he did that experiment. So then Rutherford, let's skip him for now. And so right now, this is kind of the early model. And so around this time, they were in the plum pudding, what's called a plum pudding model, and just to make you hungry right before lunchtime. And so at the time, you know, they didn't know what was going on with the electron and with the atom. So they're just kind of assuming that there's electrons everywhere, and maybe there's other stuff in there. They don't really know, but this is what they're guessing it looks like. And so Rutherford, he decided, well, let me probe this structure and see what I can determine. And so he's trying to confirm this model. And so his experiment is set up like so. So he has a source of radiation, and then his plan was to pass it through this gold foil. And so what he's expecting is, again, he's trying to map out this. So if we're looking at our plum pudding, he's going to pass a beam through it, an alpha source. And so he's kind of expecting it to be, you know, deflected, or it'll kind of go off course, expecting some sort of scattering pattern. So what actually happened, and this surprised them, and we can see a text here. So he ran his beam through, and he found that most of the alpha particles just went through with no problem. So this kind of confused them, because if we're going with the plum pudding model, it should be running into a lot more things. So most are passing through. So that's one telling us that the atom is mainly empty space. And so that's something that we know is true today. But then what also really surprised him is that some particles were deflective and bounced all the way back. And so meaning that he must have hit the nucleus with those. So he hits high density, and then those ones that hit the nucleus are reflected right back. And that was really surprising, because he was not suspecting that they would be reflected right back at him. And so from that, he's realizing that we have, you know, some sort of low density atom, and that most of the mass is just in the center here. And so again, at this time, they don't have a concept of protons and neutrons yet. It's just there's something in the center with a bunch of mass, and that's reflecting back my alpha particles, while most of them And you can see right here, most of them were just passing straight through unless they hit that nucleus there. So that was pretty surprising. And so now we're kind of here in history. And so now we have, okay, most of the atom's mass and its positive charge is contained in the small core called the nucleus. Most of the volume of the atom is empty space, throughout which tiny negatively charged electrons are dispersed. And again, we'll get into more how are they dispersed as we delve deeper into quantum. And there are as many negatively charged electrons outside the nucleus as there are positively charged particles. And again, the key point is that your atom is electrically neutral. And so next up is, okay, this model is highly successful and it still gives us at least a good basic understanding of our atomic structure today. But we still don't know anything about the neutron yet. So right now it's just been clumped in with the proton. And so Rutherford and his student Chadwick demonstrated that they found the neutrons. So what Chadwick did is he set up an experiment. So again, we have a radioactive decay of polonium. And so the radiation showed high penetration through a lead shield. And so at that time, they didn't know like what is penetrating this shield. And so that from there, they concluded that it had to be neutrons. And so they were, again, kind of elusive since they have no electrical charge. So they had trouble figuring out that the neutron and the proton were different. But again, through the radioactive decay experiments, they surmised, well, we have some sort of unknown particle that's passing through, and so they were able to, again, identify the neutron. And so that leads us back to here. So in summary, atoms are composed of all subatomic particles, so protons, neutrons, and electrons. So this goes back to our AMU, and maybe we could do a quick derivation. So protons and neutrons have nearly identical masses. So the mass of a proton is 1.67 times 10 to the negative 27. Neutron is 1.67 times 10 to the negative 27. And the mass is 9.1 times 10 to the negative 31. Hence why we just consider that negligible. So we just add up our protons and neutrons to give us a mass of one individual atom. I think we went over this on Monday, or last week. All right. And so let's see how we get here. So this is also equal to 1 atomic mass unit. And so now let's answer a few questions. So why does the mass on the periodic table work for AMU and a mole? And this also kind of gives us Avogadro's number. So how we get Avogadro's number. And so again, this keeps cropping up, so let's go over it. So it was based off of carbon, and so they wanted this to work out. So basically, if we add up our protons and neutrons, we'd get a mass of 12. And so it's based off of carbon. And so we just finished saying that for our masses, we can add up, and this is for one atom of carbon. We have 6 protons plus 6 neutrons, and that gives us carbon 12, and so that gives us a mass of 12 atomic mass units, or this number. And so we could do and so basically what we're trying to get at is if we have 12 atomic mass units, we'll probably have to convert that. So we'll convert this back to kilograms. But then we're asking, well, what factor do I need to multiply by? And this is our Avogadro's number. What factor do I need to multiply that by such that 1 mole is also equal to 12 grams? And so now we can do some conversions for a second. So if we have 12 atomic mass units, I'm just going to multiply it by roughly the mass of 1 proton, so 1.67 times 10 to the negative 27. And then, so this would give me 2.00 times 10 to the negative 26. Now this is kilograms. So that's going to be equal to 2.00 times 10 to the negative 23rd grams. And I'm just going to rewrite this. So now we're here. So I have my mass of carbon 12 is equal to 2 times 10 to the negative 23rd grams. Again for 1. So mass of 1 carbon atom. And so if we want to get to 12 grams, we need some sort of factor here. And so let's divide. So 12 divided by 2.004 times 10 to the negative 23rd here. And so what do I get for my answer? I'm a little off because I did some rounding. But so this number is 5.98, but really what I'm going for, so Avogadro's number, right, is 6.022 times 10 to the 23rd. And so we can see that's how they got Avogadro's number. If I had been more precise with my math, that would give us closer to the value. But so when solving, right, we got about 6 times 10 to the 23rd. But that's where Avogadro's number comes into play. And they have refined these last 2 digits. So I'd have to look up the most precise value. But that is, again, what it's based off of. So does that make sense why that works out? So that's why you can look at the periodic table and it matches to 1 atom and 1 mole. And then that's where Avogadro's number came in, because they wanted a nice, easy factor to get us from, again, AMU to grams. And so we'll talk more about the mole as we continue. And so now looking, and this is where I say we're all over the place, so back to the periodic table and understanding how they're arranged. So elements are defined by their number of protons. So this is really important. So if you change the number of protons, you change the atom. And so whatever you need a star, so the number of protons defines the element. And so we don't often change the number of protons, but if we're looking at, nuclear reactions, that of course is when you would see that, any such sort of radioactive decay. And so if we go back to our periodic table, right, all these numbers here in our upper left corner, not only are they the atomic number, but again, they correspond to the number of protons. And so the atomic number is also defined by the symbol Z here. And if we zoom in So our little helium atom, so we have our representation here. So we have 2 protons in red in the nucleus, and then not labeled are the neutrons, but again, we could mass them all up. So 1, 2, 3, 4. That gives you a mass of 4 atomic mass units. We look over at helium, so 4 atomic mass units, 2 protons there. And then we look at carbon. So shown here is carbon 12, and we can tell since we have 6 protons, so 1, 2, 3, 4, 5, 6, and then also 6 neutrons, 1, 2, 3, 4, 5, 6 neutrons there. And so look, carbon 6, so it's element number 6, that all matches. And so of course they're arranged by their atomic number, but then they are also arranged in a specific order, so they are arranged by columns. So these are either called families or groups on the periodic table. And so again, they're grouped that way since they have similar reactivity. So we've kind of touched on that, like the alkali metals. And so you see them on their periodic table with their chemical symbol, and then should have a name and a mass, and again, their atomic number. And so now let's look at isotopes. So can you all think of any examples of isotopes? So neon, so that's the example we have here. So looking at neon, and there's different ways to indicate it. So this is very explicit how they've drawn it here, but I've seen more like 20 neon, 21 neon. And so let's see. So they all have to have the same number of protons, but then they differ in the number of neutrons. So again, isotopes are elements with just varied numbers of neutrons, and that means that they're going to have different masses. And so they're usually named by their mass. So in this case, so protons, neutrons, we'll do electrons. So how many protons are in neon 20? So 10. How many neutrons? So 10. So 10 plus 10 gives us 20. And then how many electrons would it have? So 10, so right now it's drawn as a neutral, and so our protons and electrons should be the same. All right, so neon 21, how many protons?
10.
How many neutrons?
11.
Electrons? Excellent. Neon 22?
10.
10.
12.
Nice. And so let's go over just some other isotopes. So other common ones are like carbon 12, 13, and 14. And so there are more isotopes than this, but just to give you kind of a flavor. So carbon 12 has about a 99% abundance. Carbon 13 is only about 1%. And carbon 14 is, of course, less than, I think it's 1 part per trillion, if I remember correctly. And so a couple of things about this. So carbon 12, this is just your standard isotope. And again, looking at the mass. So the mass, you notice, is also very close to carbon 12, so that makes sense. So this atomic mass that's listed here is really just an average mass. And so what we're saying is, let's say we had, 100 carbons that we could individually put on a scale. And so that would mean that 99 of those carbons would weigh 12 atomic mass units. Then you have one that's 13, and that kind of gives you that average of 12.011. And so carbon 13 is really important in chemistry, so this is what's used for carbon NMR. And so NMR is really important, especially if you go on to like OChem or you want to characterize any sort of molecule. And usually we do proton NMR, but for organic compounds you would also want to do carbon NMR. And so NMR just stands for nuclear magnetic resonance. NMR is just basically a huge magnet, like, you know, this big around. You put your sample in the magnet, it aligns everything with the magnetic field, then it relaxes, and that relaxation gives you a nice pretty picture of a bunch of peaks that represent what your structure looks like. And so that's really important, but again, this low abundance means that it's kind of difficult to use, but now they've kind of refined the instruments to detect carbon-13. And then carbon-14, does anyone know what this is used for? So anytime you have, so this is, it's radioactive, but have you heard of carbon dating? So this is the isotope that's essential for carbon dating. So carbon-14 has a half-life of 5,730 years. And so you can compare, so if you're a living organism, right, you're incorporating carbon regularly into your body, and of course it would be incorporated at this ratio, so of its abundance. Then once you die, so you're no longer incorporating new carbon actively, and so you can compare the ratios then of carbon 12 to 14, and then compare that as it is now. So if you're looking at an old sample, you would expect it to have, right, smaller amounts of carbon-14 as it decays. And of course, there are limits. You can only go back so far since it has a half-life of 5,000. I think they use like uranium or something for dating back farther than that. All right, blah, blah, blah. All right, so we may have to end here. So I think we'll pick up on Thursday with the rest of the isotopes. So again, we'll chat more and finish up isotopes, and then we'll start working on chapter 3. And then again, I will happily take homework, labs, and then if you want to get new homework, grab it on your way out. I'll put it up at the front. Yeah, and then I will see half of y'all in the lab at once.
I'm Jacob. We spoke on the phone last week. I just had a couple questions. I didn't get the homework done. I wasn't